We've got Edo here today, who's an astrophysicist, PhD student, and most of his free time he simulates the universe in computers and attends scientific meetings. So, hi Edo, could you please tell us what an astrophysicist really does and what sort of intellectual values do they follow?
Actually, it's a very good question because the profession of astrophysicist itself is very general in the sense that an astrophysicist can specialize in many different fields. For example, I specialize in cosmology, and I do theoretical astrophysics, which means that I don't directly use telescopes. But for example, most astrophysicists as well also use telescopes, and those are observers. An astrophysicist in itself, it depends on, what subject are they actually looking at. For example, in my case, I'm looking at cosmology. So I do a lot of simulations with supercomputers, and occasionally, of course, as we need to work in academia mostly, then, we also have commitments, for example, like teaching and all these kind of things. Most of the time, we try to do research, but we always need to devote some time to teaching as well.
Very untangible, very digital. It's almost like asking a biologist, so you're a biologist, what do you do? It's just a huge subject. So it's mostly computer-based, what you do, right? It needs a lot of programming, it's very technical, is that right?
Correct, which is also, why it can be sometimes hard to actually convey what we do in research also into outreach, because there are some topics which are well established into the outreach community, into the communication towards the public, but some of the forefront research, then I would say it's pretty technical, so it's not very easy most of the times to convey it to outreach projects.
It's not for the mere mortal, studying creation and such. A big subject of what you're actually researching and simulating is, the shape of the universe, as they call it, or the cosmic web. Could you tell us about that? Because although there are some very catchy movies about it on National Geographic and Discovery, I would like to hear it from, an actual person having first-hand access.
I don't really do research on the shape of the universe as a whole. For example, if the universe is closed or if it's open, for example. So this is the grand scale of cosmology that is trying to study the universe as a whole. So what I do research on is mostly looking at the structures or dark matter, for example. So which is also related to what you were mentioning, which is the cosmic web. So the cosmic web, we know for a good 20-25 years that the cosmic web is actually the skeleton that holds the universe together, governed by gravity mostly. So what we know is that there is more or less 76% of the universe, so the matter in the universe, is composed by the cosmic web, which forms the skeleton, and then more components, for example, like baryonic matter, which is, for example, stars or ionized gas, then these components, they also follow the gravitational structure of the cosmic web and also form, for example, galaxy clusters and galaxies and so on. The main force that we'll be focusing on is gravity here, because gravity is a long-range force between two particles, no matter how far away they are. They're basically going to be influenced by gravity. But also, there's a lot of matter in the universe, so gravity is really sensitive to the presence of matter. So this is why gravity reshapes the universe. On top of gravity, there are also other physical processes. For example, there is star formation, which is not explained by gravity alone, which is also explained by nuclear physics, for example, which we don't actually simulate in our simulations. It's pretty complicated, and we don't have essentially big enough computers to actually do everything. But it's definitely something that is important, and we need to model somehow.
Yeah, it defines the world in a way. I wish there was more education, even in high school, about this, to be honest, because it all makes sense, but it also sounds strangely new. This is going to be a little bit of a subject jump, but you did mention, I don't think this is very commonly known, I don't know what it is, angry universes before. What are angry universes, Edo?
The universe in itself, I would consider it, as a pretty dynamical environment. There are a lot of things happening on different timescales. For example, some things are not gonna happen in timescale of a year, but for example, we know there are a lot of galaxies merging, and this is a really, I would say, can be a really violent process, or galaxy clusters forming. These are violent processes that can determine, the disruption of the galaxy. Or so the universe, if you want to call it like this, then it's angry. But it's also, in particular, it's very dynamic. Okay? This is why we need simulations to capture it, because we can't really track everything with calculations by hand. Okay? So this is why we need supercomputers to capture things happening on very long time scales. For example, the collapse of the cosmic web. It's relatively easy to do, but it happens on very long time scales. But there are also very short time scales events. For example, the ejection of energy from a black hole, that's something that happens in a very short time scale, which means that it's really hard to kind of have a long-term development of a structure, but with a very, very fine time resolution. Okay, so this is one of the biggest problems, I would say, in cosmology simulations.
So it's angry and energetic. Does it need a certain anger level for the universe to be like ours? If it will be less of that chaos or more of that chaos, would that have not resulted in this sort of what we're experiencing now?
Very good catch, actually. So there's a project which is led by some of my collaborators in University of Helsinki, which is called Sibelius. So normally when we simulate the universe, then we're not actually simulating the real universe, because the universe we know is started from a random field of matter, then collapsed and formed the cosmic web. But the real universe is not the universe that we simulate, because we assume different characteristics of the randomness of this primordial matter distribution. Okay, so we don't actually simulate the real universe unless we can tune the random matter distribution to retrieve some of the structures that we observe today. For example, and this is exactly the purpose of this Sibelius project. They kind of made several maps of the initial matter distribution, and then what they actually did is that they kind of matched some of the structures that we observe today. For example, like, the Milky Way, the Andromeda Galaxy, or the Virgo cluster. And once they've done the simulations, then they look for these three objects at the right configurations, and they can pick the initial matter distribution that originated something that resembles the universe today. So this controls the level of chaos, if you want. So if you want the level of chaos that contributes to the formation of the universe as it is today, then there's no more chaos in a simulation which doesn't involve that universe versus a simulation that does involve that universe. Okay, so the intrinsic chaos, the physical chaos, is always the same. Physical processes are always the same. But there's also chaos on different levels. For example, like these physical processes, they're not chaotic in themselves, which means that they're fully deterministic on a theoretical level. But the fact that there are so many particles to keep track on the simulation, so if you want the matter resolution, if you want to resolve structures of galaxies, for example, you need like very, very small particles. And these particles is like doing an n-body simulation, but when n is of order of billions or trillions of particles. Okay, this is why we need supercomputers to do this. And this is why we can't do it by hand, because it was proved already mathematically by Poincaré, basically, that already a three-body problem can be chaotic, let alone, having a trillion-body problem is going to be pretty hard to keep track by hand. So this kind of randomness, this kind of chaos that is intrinsic to the problem, to solving the problem strictly, then this is also something that is present no matter which initial conditions of the universe you choose.
I love you mentioning you cooking up a universe, and it is only really scientific, right? If it adds up to your current reality, then you figured something out. On a more subjective note, what you're discovering about the universe on a scientific level, on a very objective level, what does it give? What does it offer to the everyday person on a subjective level about a worldview?
This is a question that has many interpretations, I would say. From a philosophical perspective, then, for example, if the universe was originated from certain initial conditions or to different initial conditions, it doesn't really matter, because we're gonna live our lives normally, as well as we did yesterday, for example. So it's not gonna change our lives in a practical level. But if you think about it, for example, like on a philosophical point of view, then it can be interesting in the sense that our existence, for example, the formation of the Earth and the formation of Milky Way, the way it is, then this is related to a very specific and fine-tuned configuration in the initial conditions of the universe. So the initial conditions of the universe were slightly different, then we probably wouldn't have a Milky Way. Well, humanity might have formed in a different environment, for example, in the Andromeda Galaxy, but definitely we would have different structures in the universe. Maybe we wouldn't have, for example, a triangular galaxy, we wouldn't have the Virgo cluster, and so on. So yeah, I would say that playing with these simulations and understanding how they work and so on, then it can give an intuition for the fact that slight variation in the initial conditions that can lead to a huge difference in the structures that we observe later on.
I think it's very valuable, especially for those people who think everything has to be a certain way and there is a good way and this is what we have to follow. We are just one of the many possibilities of what we could have become. Now, from subjective to personal now, you might not find any issues in this, but I do find space rather scary. Just looking at it is just incomprehensible, hostile for me to survive in. So how do you handle that when you're examining this vast, almost like superhuman thing? Is it scary for you? How do you experience it?
For me, like in my job, there are scarier things which make me forget the less scary things. For example, like a simulation crashing for a reason that I can't understand, that is more scary than
Not
another
bad.
So, but you can eventually get used to if you're working with these timescales, like so long. But of course, like our daily experience is not made in a way that we can comprehend light years. Okay, so we have experience, for example, like if you walk from your home to a park, then you can walk for a kilometer or 2 kilometers. So you have an actual experience, direct experience of the kilometer, and this is how you perceive a kilometer. So if you're a hiker or a mountaineer, then you can also walk for maybe 50 kilometers, 100 kilometers. And this sets your experience. But already, if you're moving like from country to a different country, then you basically just get in on a plane door and you get out from a plane door, but you don't have direct experience of the trip. So for me, then the way I would see this is that it's not gonna reflect your direct experience. And the same thing with light years. So we don't have a tangible way of defining, of understanding on a personal level a light year. Okay, but we just use it because it's convenient. You don't want to quote every measurement that you do in the universe in meters, because it would be a number to such a high power. For example, like in my simulations, we don't even use light years. So light years is something that people studying the Milky Way do, because they're more comparable to the unit scale that the Milky Way is enclosed in. But we use parsecs, which is 1 parsec is 3.26 light years, so it's not much different conversion. But we use megaparsecs, which is like millions of parsecs, which is basically like 3.26 million light years. These are the scales where you start seeing the cosmic web. So if you zoom in on a very small scale, like of a light year, then you don't see the cosmic web. You see maybe a dwarf galaxy, or you see like a spiral arm of a galaxy. But when you zoom out on a very large scale, then you start seeing the cosmic web, which is basically, one of the biggest expressions of the large scale structures of the universe. Doing this scale jump can be pretty scary, can be pretty upsetting, maybe, or it can be very intriguing.
I don't think you can imagine how valuable this was for me, because you're obviously a person on the scientific field and I'm a creative. So I think what got the best of me was my imagination, that, oh, this is relevant to me, this is relevant to me, this is scary. But you're right, most of it will have nothing to do with my human experience ever out there, what we're seeing out there. So touchy, unscientific subject, this one, but unfortunately science does get watered down sometimes, especially on social media. And there is like word going around that the universe is, conscious, and there's a universal consciousness out there, or that the universe is shaped like a torus. There are like spiritual memes out there that are like, I don't think they are representing you very well. So I thought I'd ask you, what do you think about those things? What do you think about the phenomenon?
Professionally, we don't really deal with this kind of theories too much, but the best piece of advice that I would give to anybody that wants to question these theories is to use the scientific method. Do you have evidence? If yes, then the claim might be probable. But otherwise, you can find a counterexample. If you can falsify a claim or a statement, then you have proof, you have scientific proof that this claim isn't true. And I would say, and my bet is that this applies to most of these claims. There also the point, which is more on a philosophical level, but it is also very interesting to talk about, is that, okay, does the universe have a conscience? Well, yes and no, because I can't, for example, falsify this, because I can't prove this wrong, because it's there are some concepts which are just impossible to prove wrong. So if you have a theory that you cannot falsify, you cannot prove wrong in some way, then there's something wrong with the theory. For example, when the theory of general relativity came out, then so many people tried to prove it wrong, and people 100 years after, they're still trying to prove theory of general relativity wrong. So having the ability to prove a theory wrong is something that determines the health of that theory. And this is also something that is intrinsic to the modern way of understanding the scientific method. So if you see, for example, a meme, or so whatever source, that you can't have evidence for its validity, but you can't even prove wrong. This is a symptom that the theory has some problems, regardless of whether it's true or false. The theory itself, its construction, might have some problems.
So we might be encountering an invisible pink unicorn on the internet. This was one of the razors you mentioned, right? There's Occam's razor, and that was one of the razors as well. If a theory can be proven wrong, then it might as well be wrong in itself. So, on a dark note, what sort of actual threats are there out there on a cosmic level? What is the most realistic threat to Earth, besides itself, of course?
Well, it depends on what timescales.
Oh.
In time scale of a year, pretty much nothing is going to happen on a cosmic level. For example, like the simulations that we run, you see variations over millions of years at least. If you have very, very good time resolution, you're going to capture, something happening over a million years, or as we refer to, like 1 mega year. But I don't think, anything is going to happen on a cosmic level anytime soon. There was some research that was basically supporting the fact that the Andromeda Galaxy is going to merge with the Milky Way at some point in the future because they have negative velocities relative to each other. So they're basically approaching. This is a very common process in the universe. So I wouldn't be surprised the Andromeda Galaxy and the Milky Way will merge. So we see this kind of merging all the time in our simulations. This is how structures form. Two galaxies which are smaller merge to form a bigger galaxy. It's called hierarchical structure formation. It's something which is pretty well understood in simulation. This is why we have big galaxy clusters today, because they formed from small galaxy clusters in the early universe that merged together and eventually form these large objects. The merging of galaxies can look like a very disruptive event. In practice, the stars will never collide because the density of the stars is low enough so if the spiral arms cross each other, for example, they would just cross each other without pretty much any interaction other than the gravitational interaction. If you look at a picture of two galaxies interacting, for example, I want to point out the antennae galaxies, which is a pair of galaxies imaged by the Hubble Space Telescope a while ago, which is it's a beautiful image. It looks very disruptive, but if you actually look at the interaction between stars, then it's not really that bad. So I wouldn't worry too much about it at a cosmic level. Then, on the scale of the solar system, if anything is going to happen, I don't think I would be the best person to actually answer that question because there are many asteroids.
So on your scale, that is the bigger cosmic scale, galaxies sort of colliding is just a very anticlimactic thing. It's really just planets passing by each other and not very cataclysmic. On a more human scale, what future do you see for international space travel? It's a very new subject these days still.
It's a good question, actually. If you want to travel in space, then there are more things you need to worry about other than the time it takes to going from point A to point B. Of course, you're always limited by the speed of light in vacuum, so you can't really beat that. And you have a lot of energy, but you need a lot of energy to kind of even approach this. If you want to accelerate people, then those are way more particles than the particles being accelerated inside the LHC, so it takes a lot more energy. So energy aside, so there's the energy problem, of course, there's a lot of energy involved in this and more energy than we can possibly produce, I would say. There are futuristic projects like LightSail, they're trying to give an answer to this. There's also the problem of time, which is basically something that the theory of relativity comes in handy because the faster you travel, the slower time passes, seen from observer. So theory of relativity comes in handy under this problem, but then you need to shield from all the radioactive particles that are in the universe. So we are very lucky on Earth to be shielded from cosmic rays. We have the solar magnetic field that is doing a big job at that, really good job at that. But also we have the Earth's magnetosphere. So this is something very important that is preventing us from just being fried by the radiation from the sun, but also from outer space. So we often hear about solar storms. Solar storms are really disruptive, and if you want to travel to Mars, for example, like you see also in a lot of movies, there is this problem of solar radiation. So if you have a coronal mass ejection or a CME, then you should seek shelter, for example, somewhere to protect yourself from this radiation. But in outer space, so outside of the solar system, that's the least of your problems, because there are a lot of radioactive particles which are much more energetic than the solar wind. They're much more diffuse, which means that there is only one particle every cubed centimeter. But if that particle hits you, then you're doomed, basically. So it's unlikely for a particle to hit you, but if it hits you, then it's not good news.
No wonder humans are not rushing to write all sorts of like legislatures to this thing, because we're just not super close yet. Well, I would like to thank you for your time. You did tell us some amazing new info, and I'm sure it broadened the perspectives of anyone who came across this conversation. Thanks very much.
I hope so. Thanks for having me, and peace.